Okay. Um, so the next character in our story is a fellow by the name of Claudius Ptolemy. Ptolemy was an ancient Greek astronomer who put together the ideas of Plato and Hipparchus and Aristotle and various other Greek astronomers and put them all together into a coherent mathematical model. And this was not an easy model. I have seen this book, and it's just loaded with geometry and calculations, and it was very, very, very sophisticated for the time. But his model was able to predict and explain the motions of the heavens, the sun and the moon and the planets and the stars, of course. He wrote down his model. Once he got a successful working model, he wrote it down into a book. And this book was the first successful astronomical almanac. And in fact, that's probably where the word almanac comes from. It's called the Almagest, which translated means the greatest. He thought it was the greatest book ever. Okay, he had a bit of an ego. But he started off his book with several assumptions. Okay, just like in sometimes a mathematical proof will start off with certain postulates that are left unproven, but you just kind of take them on faith. He started his book with several assumptions. The first one was that the heavens consisted of nested rotating spheres. It's kind of like, if you can imagine, if you've ever seen those Russian dolls where you open up one, you get a smaller one, you open up another, you get a smaller one, you open up another, you get a smaller one, and there's a little teeny tiny one in the very center. Well, if you can imagine a spherical version of that, kind of like this, okay, where you have the outermost sphere of the stars, and then inside you have several spheres that hold the planets and the sun and the moon, and in the very center it holds the earth. Now this is a very simplistic artistic rendering of that. It doesn't have all the planets and it doesn't have all the details of the model. But the basic idea is this. You have these nested rotating spheres. They were all made of quintessence, and at the center was a stationary earth. Okay. The earth was spherical, but it was motionless. Okay, it was a motionless earth at the center, which agreed with Aristotle's ideas of the earth not moving, and it was in the middle. Also, agreeing with Plato's ideas, we have heavenly bodies moving around with uniform circular motion. Okay, so there was uniform circular motion around the center, and that he would use this to describe the heavens. This is very important because it turns out he ended up violating his principle of uniform circular motion without actually saying so. He tried to make his model work with uniform circular motion. It didn't quite work. It didn't agree exactly with the motions of the planets, especially the planets. And so instead of throwing it out, he sort of patched it together. He kind of cheated, really. And that's only important because that's one of the things that Copernicus was very concerned about later on, many, many centuries later. Nobody much really cared that Ptolemy had done this because his model was so successful. But Copernicus eventually was concerned about this. So now he had trouble explaining the irregular motion of the planets. Okay, he used some very, very unusual geometric devices to try to explain this. Okay, so let me see if I can draw what Ptolemy's model was. Okay, you had the Earth at the very center of the universe. Okay, surrounding it at the very edge was the celestial sphere. So the stars were very, very far away. Okay, and that was the outermost sphere, as you saw in the previous page. This is not nearly as nicely drawn, but I need to show you how it works. Okay, and basically the celestial sphere would go around the Earth in this direction every day, every 23 hours and 56 minutes, and it would drag along everything else with it because inside were the spheres that held the sun and the moon and the planets. Now, the sun was no problem because the sun, we'll say that this is the sphere holding the sun. You remember that the sun would jump 1 degree to the left every day. Okay, so the sun would go like this, 1 degree per day. And do you remember seeing that on the dome? that it would make this little 1 degree jump every single day. We know now that that's because of the Earth going 1 degree around the sun each day, but that's not what they believed. Okay, Ptolemy believed that this entire thing went around the Earth clockwise, and at the same time the sun would slip 1 degree counterclockwise relative to the stars each day. Now that was no big problem with the sun because the sun always went eastward relative to the stars. Its sidereal motion, if you remember, was always eastward 1 degree per day. The moon would do the same thing, except it would jump 12 degrees to the east. So the moon, for example, would maybe be around here, and the moon would jump 12 degrees per day. Okay. However, that was not the case with the planets. The planets were much more complicated. So what we had to do with the planets, what Ptolemy had to do with the planets is make some way of having them sometimes go backwards. Because you remember, planets are the objects that would do retrograde motion. Okay, so the planets would sometimes, most of the time they would go eastward relative to the stars, but sometimes they would go backwards. So what Ptolemy did was, instead of putting a planet on a main circle going around the Earth like this, he made a little secondary loop. The planet would be on this little secondary loop that would turn this way. At the same time, it was being carried around by the main loop this way. Okay, so the planet basically would be on 2 circles. It would be almost like on gears. And the secondary gear, which was called an epicycle, would carry it around at the same time that the main circle, which was called a deferent, okay, would move it around the Earth counterclockwise relative to the stars. And again, the whole thing would go around the Earth once a day, but at the same time the planets would be slipping relative to the stars on these secondary loops. The neat thing about this was, if you trace out the motion of the planet, what would happen is this. The planet would most of the time go this way as seen from the Earth, but then every now and then it would loop around like this, and that would be the retrograde loop that you remember seeing on the dome. And then it would stop and go back in the same direction. So you had the prograde motion explained very nicely, and then you had the retrograde motion explained very nicely. Okay, this was a tremendous accomplishment because he was able to have an Earth-centered model where the planets sometimes moved backwards, but he was able to still use perfect circular motion, uniform motion in a nice circle. Or at least he thought he was, at least at the beginning he did. Unfortunately, there were some complications. For example, the prograde motion on one side of the Earth would be a little bit faster than on the other side. So what he did was he said, well, you know, it's okay if the Earth is still in the middle. We'll just not put it directly in the center. So here's the center right here, and we're going to put the Earth slightly off to the side, okay, like that. So he moved the Earth off to the side, and that's called an eccentric or an eccentric, depending on your pronunciation. We still call people who are a little off-center eccentric today, right? That's where it comes from. So the entire Earth was shifted a little bit to the left or to the right or whichever, depending on the planet you were talking about. And that helped even out the prograde motion to match more the way it was observed. The other thing was a little trickier. What he said was, you know, sometimes these retrograde loops last longer than at other times. The only way I can make that work is if I put another point in here. And I'm going to call this point the equant. Okay. The equant was a point that was not in the center, and it was not at the Earth, but it was the point around which the planet would rotate uniformly. The planet's deferent would rotate uniformly around the equant. You know what? That is basically cheating. That is not uniform circular motion around the center anymore. So what Ptolemy was doing was he was saying that he was using uniform circular motion, but in fact he was cheating. He was saying, and that's really the only important thing you need to know about the equant. The equant is a very complicated sort of concept, but the point is that he was saying he was going to use uniform circular motion, and he didn't. The thing was, his model worked so well for so many years that nobody really cared, or at least the people who did care didn't make much of a fuss about it. Okay, but that was the basic model, and it was so successful for over 1,000 years. People used his model to make predictions about the planetary positions and the motions very, very, very well. Okay, so there it is again in a slightly neater form. So the epicycle and the deferent was where he put the planet on a secondary circle, turning on the primary circle, and the main point of that was it was to explain the retrograde motion. So the epicycle was there to explain retrograde motion, and it did so very, very well. The sun and the moon did not have epicycles. Only the planets did, because they were the only ones that did retrograde motion. The eccentric offset the Earth from the center to explain variations in prograde motion. Okay, again, details you probably don't need to know about exactly why it was there, but it was there. And the equant, very, very weird. It offset the center of uniform motion from the geometric center to explain variations in retrograde motion. Sometimes the retrograde loops would last longer than others. The important thing again, though, and this is the thing, the important thing here is the equant violated uniform circular motion. It violated the assumption of uniform circular motion, and that's why it's important to us. Okay. One other thing about Ptolemy's model. Here is a summary, sort of Ptolemy's model, and a very nice drawing. You have the Earth, and then the outermost part is the sphere of stars, and then you had Saturn and Jupiter and Mars. Their epicycles depended on how big of a retrograde loop they would make. Then you had the Sun, then came Venus, Mercury, and the Moon. By the way, this is not in the right order, of course, because Mercury is actually closer to the Sun than it is to Earth, but Ptolemy got that wrong. He didn't know the distances. He didn't know how far apart the planets were spaced, because the Earth was stuck more or less in the center, and so you only got one view of the planets. But notice the Moon and the Sun don't have epicycles, but the planets do. However, here's a very, very important point. Mercury and Venus always stay near the Sun in the sky, right? You remember that from last chapter? Well, we know now why that is, because their orbits are actually closer to the Sun than we are. They're inside the Earth's orbit, so naturally they stay close to the Sun. Ptolemy's model had no such restriction, however. So what he had to do was he had to invent a restriction. He said, Mercury and Venus seem to follow the Sun, so I'm going to restrict the center of their epicycles to always be along a line between the Earth and the Sun. So that as the Sun went around, Mercury and Venus would follow along this imaginary line. Kind of weird. He never gave an explanation as to why that would be. You might think, well, maybe it's because it was poised between the Earth and the Sun. But the Moon had no such restriction, so who knows? Okay, but this is going to be very important, especially if you look at the epicycle of Venus. This is going to be very, very important when we talk about Galileo and his discoveries with the telescope. Okay. So Venus and Mercury were forced to always be on a line, or at least the center of their epicycles were forced to always be along a line between the Earth and the Sun. And so Ptolemy's model was tremendously successful. Every few decades, a new set of tables was made up so that it would predict the positions of the planets. They were called the Prunetic tables. Everybody was happy with it. It survived the Dark Ages, survived the Middle Ages, and it wasn't until the early 1500s when it finally came into questioning. And that was by a fellow by the name of Nicholas Copernicus. And that is the person we will talk about in lecture next time.